initial interest was on making active particles, but we've kind of gotten into other areas that I'll describe. Okay, and that's what you're seeing in this video on my slide here. These are ensembles of catalytically active Janus particles. Okay, so before I start talking about the work, I should give a thank you to the people that actually do the work. So this is my group. The ones highlighted in red are really the ones that contributed to this work. Aiden, who's a postdoc in my group now, he did his PhD with me. Before that, he has done a significant part of this work. And then Marola Isa, she was an undergrad at Cleveland State who did her undergraduate research with me. And a lot of what I'm going to show is actually her work and experiments. She is now a PhD student in my group at Case. And then Mohammed Khalil, he's the other person I should give a thank you to, because he also was an undergraduate researcher in my group at Cleveland State. He graduated and he's now on to greener pastures. So I just wanted to highlight, so I recently moved to Case, but I want to highlight Cleveland State just because most of this work, actually all of this work, was done while I worked there. But in January I moved to Case, and then obviously because of the pandemic, we haven't really done much since March. So okay, so what do we do? So our group in general is interested in non-equilibrium and crowded colloidal suspension. So all of the systems we work on are basically particulate systems and fluids that are somehow far from equilibrium, or they're crowded in some way. I won't go through each of these, but I'll just highlight the two things on the left here. So we have a whole selection of work in active and driven colloids. And we also have some work in dynamics and interactions near boundaries. So work where we're specifically interested in measuring the conservative interactions that a particle feels when it's near a boundary. And these things are connected, as I hope you'll see by the end of my talk. The thread that really connects these two umbrellas of work is, or I should say, are anisotropic features of particles, or anisotropic particles. So that's really a kind of one of the fundamental legs of my group, is that we're very interested in anisotropic particles that have some non-uniform property along its surface. This could be chemistry, this could be curvature in the sense of like an anisotropic, geometrically anisotropic particle. This could be optical properties, it could be mechanical properties. So our strategy for kind of attacking the selection of problems in this area is to make model systems. So we make model systems in our lab. We make ellipsoids, we make doublets occasionally, we make Janus particles. And we utilize these systems to mimic technologically relevant systems that could consist of paint additives, biological colloids, red blood cells, or fungus, for example. And we have some collaborators where we work with them on projects that utilize these more technologically relevant systems. But we, our real expertise and our focus are in Janus particles. So about 2.5 years ago, we started making these Janus particles in our lab. And as Chloe mentioned at the onset, there's a whole real kind of zoology of Janus particles now. I mean, I think probably the original idea here with Janus particles was this hydrophilic, hydrophobic, spherical particle. But now the field, I think, has really grown to encapsulate many different types of geometries and ways of thinking about a particle, the Janus. So metal cap Janus particles, that's one kind of, I would say, type of Janus particle. And these are made, from glancing angle deposition. You can make these patchy, or you can make them Janus such that 50% of the surface coverage is a different composition. There's also these polymer composite Janus particles where you actually have, rather than having a sphere with a cap, you actually have two regions of the particle that are kind of like, it's a composite particle where one region is one material and the other region is a different material. And then a more recent kind of, bit of work came out a few years ago on making actually graphene sheets Janus. And what's kind of interesting about the graphene sheets is that they really act as effective surfactants, as you might expect being a Janus particle, but you get the added functionality of the graphene as well. So you have the functionality of the Janus particle in terms of its surface activity with fluid-fluid interfaces, but then you also get functionality as a consequence of it being a 2D material. So I know there's groups now utilizing these types of materials for energy applications and separations and things of that nature. So there's a whole zoology, but I'm not going to be talking about that. I'm going to be talking about basically metal-capped Janus particles. And really, in our lab, what we do is we make either platinum or gold, as I'll describe, gold capped Janus particles on polystyrene beads. Okay, so we utilize polystyrene beads as kind of the base for many of our systems, and that is true also for our Janus particle system. So first I want to start with an experiment that we did a couple years ago. So what I'm showing here is an illustration of a Janus particle. This is a platinum capped Janus particle. It's platinum on polystyrene. Nominally, the particle is 5 microns in diameter, and it's in water. If you take a video of this system, then you see that the particles experience Brownian fluctuation. If you add a bit of peroxide, then they start to propel. Right? This is an observation that now is 15 or 20 years old at this point, but this is part of the experiment that we do. You add a little bit of peroxide, and they, as a consequence of the decomposition reaction, begin to propel. And then if we add nanoparticles, so if we add 20 nanometer polystyrene beads, again, it's kind of similar surface chemistry as the native polystyrene bead for our Janus particle, then their propulsion stops. Okay, so this was an experiment we did about 2 years ago, and it was done by Marola, and we were kind of curious as to why this was happening. So just to kind of summarize, we get, you put this Janus particle in water, no propulsion, add some peroxide, there's propulsion, add dispersed nanoparticles, and there's reduced to zero propulsion. So we make these particles, as I mentioned, through this glancing angle deposition. For this particular type of Janus particle, we evaporate platinum onto a monolayer. We desorb these Janus particles and we disperse them in whatever fluid we're going to utilize. We can characterize them. This is kind of just a neat thing that actually has an impact, which I'll talk about at the end of my talk, but we can use E-beam lithography to cut this particle in half and then measure how the cap thickness varies. So oftentimes when you draw Janus particles, I do it, you draw it with a uniform cap, but indeed if you do the measurement, then the cap, as you might expect from the deposition process, the cap actually decays to a 0 thickness near the equator, and at the North Pole, you get the nominal thickness that you might expect. So if I say the cap is 10 nanometers, that just means that the cap is 10 nanometers thick at the North Pole, but it decays to 0 near the edge. And like I mentioned, this was kind of just an interesting thing that we did a couple years ago, but it actually does have an impact, which I'll describe right at the end. Okay, so that's how we make them. And then this is the basic experiment where you can systematically, for example, change the peroxide concentration. And you can see from these videos that as you add peroxide, as you increase the peroxide concentration, the speed of these particles increases. And that's nominally because there's this decomposition reaction for the peroxide where you generate solute gradients across the length scale of the particle, and then as a consequence, the particle propels because of diffusiophoresis. There are other effects that might contribute to this locomotion. We're starting to get more interested in that now, specifically what kind of chemistry can be adjusted on this platinum cap. I don't have much to say about that right now, but just nominally, it's how you should think about it. You have peroxide, it decomposes, it propels the particle, so as a consequence, you get this concentration dependence. And indeed, you can measure how the mean square displacement changes with peroxide concentration, and you can basically nominally kind of measure how the speed increases with peroxide. So that none of that is really new for us. That's been observed before. The thing that is new, though, is that when we add, so if we add these nanoparticles, so these are these polystyrene 20 nanometer particles, then we see this quenching. So this is a typical mean square displacement you see on the left-hand side. The open circles are with no nanoparticles. The black circles are with nanoparticles. And for those of you who might be new to the area, so in order to characterize the speed of a propelling particle, you measure the mean square displacement. If the mean square displacement depends nominally on the square of the lag time, then it's propelling. If it's linear lag time, then it's just typically Brownian fluctuation. So we're going from this kind of parabola MSD to a flat MSD, which is the first sign that there's some kind of quenching happening as a consequence of the addition of these nanoparticles. And then actually, if we do this for a few different depletant concentrations, we see that basically as soon as we add depletants, the speed goes to zero. They're not stuck, right? The particles are still fluctuating. It's just the speed has dropped significantly. So my collaborator at Cleveland State, he's a mathematician, and he does agent-based simulations of active systems. This was kind of our first attempt at trying to understand this. So our hypothesis here was that when you added these charged nanoparticles, you induced what's called a depletion attraction between the Janus particle and the boundary. And then as a consequence of that depletion attraction, you bring the particle closer to the nearby boundary, and that would reduce the swim speed because of decreased mobility of the particle. So we simulated this with these agent-based simulations. We essentially put in all of the necessary physics when it came to hydrodynamic interactions with the nearby boundary. And we found that indeed, as you decrease the separation distance of the active particle, the swim speed would also decrease. Okay. The problem, though, is that even though, and this was primarily just a hydrodynamic explanation, right? So you're moving the particle nominally closer to the boundary. That's increasing the hindrance experienced by the particle or decreasing the mobility of the particle, and you would expect it to move more slowly. So that's really a hydrodynamic explanation. And it does reduce the swim speed, but not to the extent that we observed in experiments. So there has to be something else going on. So the thing that was pointed out to us about a year ago is that one of the effects of adding solute, whether it's a nanoparticle or salt, for example, is that you might alter the conductivity, and it's been observed that conductivity indeed slows down swimming. This was from 2014. That if you added salt in this particular contribution, if you added salt to this active catalytic active system, that you would reduce swimming. And indeed, actually, these charged nanoparticles that we're adding were altering the conductivity to some extent. So in response to that, what we did was we, rather than using these 20 nanometer polystyrene beads, we chose to use PEG as the depletant. So we chose a couple different molecular weight pegs in order to separate the effect of depletion attraction from that of conductivity, because a sufficiently low molecular weight PEG will have a negligible impact on conductivity, whereas a higher PEG would have a larger impact on conductivity. So what I'm showing here are basically two sets of data. One, we have apparent swim speed as a function of depletant volume fraction as a consequence of the addition of a low molecular PEG that again has negligible impact on the conductivity. And then I have another set of data where we added salt. And indeed, in both cases, we do slightly decrease the swim speed. And even in the case where we added PEG as simply a depletant with no influence on that kind of conductivity, we decreased the swim speed. So it appears right now that there's an impact of both mechanisms. There's an impact of the proximity of this particle to the boundary, and then there's also this known impact of conductivity. So then we started to move on to ensembles. So all of the experiments that I showed you up till now have been essentially infinite dilution, where we have particles that are not near neighbors, and we're simply measuring the nominal speed in response to depletants. But obviously, when you're or maybe not obvious, but when you're utilizing these active systems, there's really a rich phase behavior that can arise when you put these particles into ensembles. So if you put particles at low to moderate concentration, you'll start to see clusters form. And indeed, this is, if you zoom in a little bit, you can see this dynamic behavior more closely. So this, I like to call this colloidal square dance, because if you watch the particles, you'll see that particles will collide and they'll see their neighbor and they might rotate a few times and then they'll separate as if they're, in a square dance. And the reason why this happens is that by making the particles active, you're increasing the probability of collision. That's the first thing. But in order for this collided pair of particles to again separate, they need to rotate away from each other, right? Because the motion is directional, so they'll have some directional motion where they collide, but then one of them needs to rotate away in order for the particles to separate. So there's this collision reorientation release behavior, and what you see actually is if you track singlets, intermediates, and clusters. So that's this is nominally how we do the experiment, where we track all the singlets, we track intermediates of these active particles, where we have the intermediates are doublets and triplets, and then we have clusters, which are considered to be 4 or more. We see that as you add peroxide, you start to increase the probability of clusters forming. So these are data for ensembles in 3% hydrogen peroxide, and we can see that the singlets, and also I should note that these data are for just a single video. So in a single video, you get fluctuations of all of these populations. So that's why singlets and intermediates have these kind of wide distribution of data, whereas clusters are a little bit tighter distribution. But anyway, so you have these singlets and you have intermediates that start to decrease at longer time, and then you have clusters that start to pick up at longer time. And if you take many observations of this process, so many videos, and then you average over the behavior, then you do indeed see that increases in peroxide increase the speed and the collision probability, meaning that the clustering in this system is enhanced. So again, this is not necessarily new, right? So people have observed clustering behavior in active systems obviously before, but what we wanted to do was to then measure the effect of depletant on these ensembles. So we did essentially the same experiments where we took, again, these ensembles, and we tracked all the clusters that formed in these ensembles, and we tracked it for a function of depletant concentration, where this depletant is in particular the low molecular weight PEG. And that what we found was that essentially nominally at the first few lower concentration depletant concentrations, there's basically no effect. So the dotted line is is the level of clustering that you would expect as in the absence of depletants. And then as we started to add depletants, there maybe was a little bit of an uptick, but then we start to see a decrease in observed clustering, meaning that you're not forming as many of these 4 or more groups in the process after you've added the depletants. So our explanation right now, and this is kind of what we're working on at the moment, is that as a consequence of the addition of depletants, you're decreasing the collision probability. So you're slowing down the active Janus particle, and because you're slowing down the active Janus particle, you're decreasing the collision probability, and therefore decreasing the probability that you're starting to form clusters. Okay, so so I think what's clear from the experiments that we've done at infinite dilution and then these experiments in ensembles is that surface interactions likely play a role, and we're not the only group that have observed this. There's been recently quite a few examples of how surface interactions, either hydrodynamic or conservative interactions, play a role in active motion of particles. So we have a strong interest in measuring these surface interactions. I'm just going to check the time for a minute. Okay. So we do this experiment in our lab called total internal reflection microscopy, which is an experiment where you measure fluctuations in a particle near a boundary. And from those fluctuations, you can calculate the potential energy profile. So you can calculate the conservative interactions experienced by that boundary. And the thing that's great about this is that it's a very sensitive measurement. The problematic thing is that it's really only suitable at the moment for spherical particles. What we're doing is we're expanding this technique to anisotropic particles, whether it's geometrically anisotropic, Janus particles, or doublets. And there could be a whole other talk on this, but I'm not going to go into it anymore. But essentially, what this experiment does is that it measures Brownian fluctuations of the particle. So really, Brownian fluctuations of these particles near a boundary are central to us understanding this TRM technique and being able to kind of optimize the TRM technique. So as a result of kind of that motivation, this last part of my talk, I'm just going to summarize some Brownian dynamic simulations that we've done for a Janus particle near a boundary. Okay, and talk about the influence of the presence of a cap on a Janus particle that has a density that does not match that of the fluid or of the particle itself. Okay, so we do these Brownian dynamic simulations with a well-known stepping algorithm that includes the conservative forces experienced by the particle, and then it includes a random displacement along with the impact of height on the diffusion coefficient on the mobility of the particle itself. So this is the stepping algorithm for position. And there's also a stepping algorithm for orientation, which includes many of the same elements. It includes this position-dependent diffusion coefficient. It can include the torque experienced by the particle, which is important for our purposes because we want to calculate the gravitational torque introduced by the presence of the cap. In the way that we accommodate, doing the simulation for a Janus particle is that we mesh the particle surface such that we can assign different properties to the mesh points on the Janus particle. So, you might have a cap that has mesh points that, for example, have zeta potentials that are different from the native particle zeta potential. So these are data these are kind of like raw data that we get from the simulation. I'm plotting observation as a function of orientation for a Janus particle that has a 20 nanometer gold cap. And this is for different particle radii. So what you see here is that there's a range of particle radii from 1 micron to 6 micron. And the observations for the 1 micron particle are quite flat, right? So this means that the orientational observations for this Janus particle basically cover the entire orientational space for that particular particle. But as you increase the size, you start to get increased probability for the cap being down, okay, which means that the Brownian orientational Brownian fluctuations of that particle are beginning to be quenched as a consequence of the presence of this cap. So we can then plot these probability distributions not only as a function of orientation but also of height. So here I'm showing three orientational, probability distributions for 1 micron, 3 micron, and 6 micron particles. From these probability distributions, we can then calculate as we would do an experiment. So this is kind of why we're doing the Brownian dynamics, is to understand how to utilize this data in a way that we can calculate the potential energy landscape. We take these probability distributions and we can calculate the potential energy, which is shown on the right-hand side. So these probability distributions then become potential energy landscapes. So these are potential energy landscapes for, you know, a 3 micron and a 6 micron polystyrene bead, each with a 20 nanometer gold cap. And essentially what you can see here is that for the 3 micron particle, you have a more shallow potential energy well, whereas for the 6 micron particle, you have a much deeper potential energy well, again, kind of as a consequence of the presence of this cap on the polystyrene bead. Because the particle in the 6 micron case is bigger, you have a stronger gravitational torque from this non-density matched cap that is causing the particle to sample more orientations down. Okay, so the thing that I'll finish up on here is the importance of van der Waals interactions. So van der Waals interactions, as you can see from my expression here, for the conservative forces utilized for the stepping algorithm, we only included in the data that I showed electrostatics and gravity. But you might imagine that van der Waals interactions have you know, a role in the interactions of these Janus particles with a nearby. So I started working with an excellent undergrad at Case. He's finishing in the spring, but he's starting his PhD at Berkeley in the next fall. And he's really a brilliant young person. But in any case, he developed this summation algorithm where he can actually take the particle, basically utilize the same kind of meshing concept that we used to assign different properties, and then utilize a summation in order to calculate the van der Waals interactions experienced by the particle. So this is just a small selection of data that we have. He has van der Waals potential on the y-axis here as a function of rotation, and what he finds indeed is that the cap coverage matters in terms of what angles will be influenced by van der Waals interaction, but it doesn't really change the magnitude at all, which is kind of, I guess, because you're thinking about an interaction that's really kind of like a near field interaction, such that it's really only when the particle rotates down such that the cap is interacting with the boundary that van der Waals interactions would really play a role. And then the last thing I want to say is very, very recently, so he has the ability to basically run this algorithm for any geometry of the Janus cap, and he started to calculate the influence of having a uniform cap versus a non-uniform cap. And indeed, he sees that there is an impact of the fact that you have this cap that decays to zero near the equator in the van der Waals interaction. You also have, I don't have the data here, but you also have a pretty strong impact on the gravitational torque as a consequence of the cap being non-uniform. So this is really kind of what we're doing now, is we're trying to understand how different cap characteristics influences these conservative interactions near a boundary. Okay, so hopefully I've convinced you that, you know, active particle speed is influenced by these surface interactions. In this particular set of experiments, it was a depletion interaction. Clustering behaviors also of active particles is also impacted by these surface interactions. That Janus particle dynamics are quenched by a non-density matched cap, and then also that the details of Janus particles really do matter to the dynamics, whether that's cap thickness of a non-density match cap or the geometry in particular. And really the thing that I'm getting excited about now is kind of utilizing some of these concepts in terms of like anisotropic particle interactions and things of model systems, so Janus particles, ellipsoids, doublets, things like that, to real, technologically relevant systems like red blood cells, okay? And then this is just, again, a thank you for the people that did the work. And I'd just like to thank the organizers again. This is really an excellent idea, I think, to have these focus meetings that capitalize on our unfortunate situation of the pandemic, but we can make things virtual and then we can come together more easily. So, and I'm happy to take questions, although we probably don't have time, but I'll be around for the discussion later.